Welcome to Chapter 4, the final chapter of the Chemoinformatics Introduction series. In this lecture, we'll explore how AI is revolutionizing synthesis planning. We'll learn to represent chemical reactions in computer-readable formats, predict reaction outcomes, and most excitingly, work backwards from a target molecule to plan its synthesis. This is retrosynthesis, one of the most impactful applications of AI in chemistry today. Before computers can reason about reactions, they need to understand them. Reaction, SMILES, extends the SMILES notation we learned in Chapter 1 to include reactions. A period separates different molecules on the same side of the reaction. The double greater than sign represents the reaction arrow, separating reactants from products. For example, Fischer esterification of acetic acid and ethanol becomes acetic acid period ethanol greater than ethyl acetate period water. Atom mapping, shown with colons and numbers, tracks which atoms in reactants become which atoms in products. This mapping is crucial for understanding reaction mechanisms and for machine learning models. SMERCS is to reactions what SMARTS is to molecules, a pattern language. While reaction SMILES describes specific reactions, SMIRKS describes reaction patterns that can match many specific cases. Consider ester hydrolysis. The SMIRKS pattern describes breaking any ester into a carboxylic acid and an alcohol, regardless of what R groups are attached. This generalization is powerful. From one SMERCS pattern, we can generate thousands of specific reactions. Template-based synthesis planning extracts these patterns from known reactions in databases, then applies them to new molecules. Think of it as encoding chemical knowledge in a form computers can use. Where do reaction templates come from? Large databases of known reactions. The USPTO database contains 1.8 million reactions extracted from US patents, and it's freely available. REACSES, a commercial database, has over 50 million curated reactions from literature. SciFinder is even larger with over 100 million reactions. The workflow is: extract reaction templates from these databases, generalize them using R groups and SMERCS notation, then apply them to new target molecules. The USPTO dataset has become the standard benchmark for reaction prediction models. With enough examples, machines can learn the rules of organic chemistry. Forward prediction answers. Given these reactants and conditions, what products will form? Modern approaches use transformer models, the same architecture behind ChatGPT, adapted for chemistry. The model encodes reactant SMILES strings, processes them through attention layers that learn which atoms interact, then decodes the product SMILES. On the standard USPTO benchmark, current models get the exact major product right about 85 to 90% of the time, and the correct product appears somewhere in their top 5 predictions about 95% of the time. IBM RxN for Chemistry offers this as a free web service. You simply draw or paste your reactants, and the model returns the predicted products together with a confidence score. Separate models can then estimate the likely yield. Retrosynthesis is the art of working backwards from a target molecule to available building blocks. You start with what you want to make, then ask, what reactions could produce this? Each possible reaction is called a disconnection. You continue asking this question for each intermediate until you reach commercially available starting materials. The result is a retrosynthesis tree showing all possible routes. This was pioneered by E.J. Corey, who won the 1990 Nobel Prize for this work. AI now automates this process, searching through millions of possible disconnections to find practical routes. The best route balances step count, yield, cost, and practicality. Two powerful tools make AI-driven retrosynthesis accessible. AI ZynthFinder, developed by AstraZeneca and released as open source, uses Monte Carlo tree search combined with neural networks to explore the retrosynthesis tree. It runs locally on your computer, works offline, and can be customized with your own reaction templates. IBM RxN for Chemistry offers a cloud-based alternative with a beautiful web interface. The free tier allows exploring retrosynthesis routes for any molecule. It uses transformer models trained on millions of reactions. For quick exploration, try IBM RxN. For integration into pipelines or custom models, AI Synth Finder is the way to go. Finding possible routes is just the beginning. We need to evaluate which route is best. Key scoring criteria include step count, where fewer steps mean less labor and lower chance of failure; cumulative yield, the product of individual step yields; cost, including building blocks, reagents, and specialized equipment; accessibility, whether intermediates are stable and handleable; and novelty, whether the route uses known versus novel chemistry. Modern tools compute these scores automatically and can optimize across all criteria simultaneously. The goal is finding routes that are not just chemically feasible, but practically executable in a real laboratory setting. Chemoinformatics opens exciting career paths. In pharma and biotech, you might work on drug discovery pipelines, lead optimization, or ADMET prediction. Software development roles include contributing to tools like RDKit, building platforms for computational chemistry, or developing new AI models. Academia offers opportunities in research, teaching, and publishing cutting-edge methods. The startup world is booming with AI drug discovery companies raising billions in funding. Core skills you need. Python programming is essential. Machine learning knowledge is increasingly required. Chemistry understanding provides domain expertise, and statistics helps you evaluate models properly. To give you a concrete anchor, a 2023 survey of the Japanese market put junior roles at 5 to 7 million yen, mid-level at 7 to 10 million, senior at 10 to 15 million, and principal scientists at 15 to 25 million, with foreign-affiliated pharmaceutical companies typically paying 1.5 to 2 times those figures. Congratulations on completing the Chemoinformatics Introduction series. Let's recap our journey. In Chapter 1, we learned how to represent molecules as SMILE strings and work with RDKit. Chapter 2 covered QSAR and QSPR, predicting molecular properties using descriptors and machine learning. Chapter 3 explored chemical space, similarity metrics, and virtual screening. And in Chapter 4, we tackled reaction prediction and retrosynthesis planning. Where do you go from here? The RDKit documentation is your best friend for practical coding. Deep Chem tutorials cover deep learning for molecules. PubChem gives you free structures and assay data to practice on. And the Journal of Cheminformatics shows you the cutting edge, with most of its papers open access. The field is evolving rapidly, and you now have the foundation to evolve with it. Thank you for learning with us, and best of luck in your chemoinformatics journey.